This conference will now be recorded.
Good afternoon, all. Now I welcome all the participants again for the day 4 post-lunch session. This session will be taken by Dr. Abhishek Dikshit. He is from Department of Electrical Engineering, IIT Delhi. He'll be talking about Li-Fi networks, in specific physical layer design of the Li-Fi network. Now I request our student Ashi to kindly say a few words and welcome sir.
Good afternoon, everyone. Professor Abhishek Dikshit received a PhD degree in Computer Science Engineering from Department of Information Technology, Ghent University, Belgium in 2014. His PhD research focused on designing architectures and algorithms for optical access networks. Before that, he did masters in optoelectronics and optical communication from IIT Delhi in 2010. Before joining IIT Delhi in December 2015, he has served for a semester as an assistant professor at IIT Mandi and as a postdoctoral researcher at Ghent University, Belgium. His areas of research include optical communications, optical networks, optical wireless networks, energy efficiency of telecommunication networks, and signal processing. Today, he'll be talking about Li-Fi networks, that is, physical layer design of the Li-Fi networks. Welcome, you, sir. Over to you.
Thank you, Dr. Jindal, and thank you all and organizers for inviting me for this talk.
Welcome, sir. Welcome, sir.
Thank you. As you know, that this talk is about Li-Fi networks, and I will be talking about physical layer design of the Li-Fi networks. So if you have some questions, you can ask me if it is allowed, or you can post your questions in the chat box. So let's start.
Yes, sir, we may.
So this is the outline of my talk. We will talk about introduction to Li-Fi, then we will be talking about visible light communication system model. Then I will be talking about multipath channel modeling and characterization. We will then see modulation schemes that can be used for VLC networks, multiplexing techniques that can be used in VLC networks, and I will then show some demos. So what is Li-Fi? Li-Fi is a light communication system which transmits data at high speed. So the focus here is on light communication. So if you see this electromagnetic spectrum, we are interested in these range of frequencies. That means the frequencies from 300 gigahertz up to 30 petahertz. Okay, so if we operate in these range of frequencies, typically these are considered as light frequencies. Okay, so there are various flavors of light communication that you can have. Either we can talk on visible light, which spans from 750 nanometer to 380 nanometer. We can have ultraviolet, which is this band, or you can have infrared spectrum, which is this band. Okay, so at present, this talk is basically about using visible light for communication systems. Okay, so that is the domain of visible light communication. So in this talk, we will be only focusing about visible light for communication purposes. So as I have said, Li-Fi is about light communication, and light communication depends upon which frequencies you choose for communication. If you choose ultraviolet, then you have a Li-Fi system which uses ultraviolet. You can have visible light for communication, or you can have infrared for communication. Typical examples of the universities where these systems are considered. So ultraviolet Li-Fi systems is considered at KAIST University in Japan. Visible light is the focus of IIT Delhi, and infrared Li-Fi systems are considered at ISC Bangalore. So if you want to read more about these systems, you can look at the Google Scholar and search for these universities, and you will get the Li-Fi papers in these particular domains. So we will be talking about visible light communication because this is our forte. Okay. So what is visible light communication? In short, this is abbreviated as VLC. It's a short range optical wireless communication technology. We cannot use visible light for a lot of kilometers. It's basically an indoor communication technology. It can be a replacement of Wi-Fi, for example. So visible light communication system operates in this frequency range. The frequency range goes from 400 terahertz to 800 terahertz. And a possible solution to have this VLC is using LED lighting. So everyone at homes is aware that we use nowadays LEDs for illumination, and the same LEDs can be used also for the communication purposes. So you would not be duplicating infrastructure, and that is the main selling point of visible light communication. If we reuse the LEDs that are used anyway for illumination, we would not be spending another cost in having the communication infrastructure. As I've said, it can provide both illumination and communication, and this is the typical example of VLC network. Okay, so we will be using LEDs, bulbs, so this will be transmitting data as well as illumination. So the first question is, why are we so much interested on these LEDs? Why the focus is on LEDs? Can we use some other sources for communication purposes? And the main reason for this is, if you look at these various sources, so at the beginning we just used to have candle, and then we have got this incandescent bulbs, then we are talking about fluorescent, and nowadays we are having LEDs. Okay, so these sources are characterized in terms of their luminous efficacy. What does this mean? That means for what electrical power, so if my electrical power is 1 watt, how much lumens this source can produce. Okay, so you can appreciate more is this quantity, better is the source, right? For example, LEDs have a luminous efficacy of 300 lumens per watt. That means for every watt that you provide to these LEDs, you will have 300 lumens. Okay, and this was only 70 lumens per watt in fluorescent, and in incandescent bulbs this was even lower. Okay, though to these candles we do not directly have some watts, but of course in manufacturing of these candles also we invest and waste some energies, and people have looked into what is this corresponding luminous efficacy of the candles. Okay, and it's very low, it's 0.3. That means LEDs are most energy efficient sources, illumination sources that we have at this moment. And if you can use these energy efficient sources for communication purposes, nothing like this, right? And that's why we are going after this LEDs. The second advantage of these LEDs is the lifetime. Okay, so they have a very good lifetime, 1 lakh hours. That means an LED bulb can operate up to 1 lakh hours without getting faulty. So it has a very small replacement cost, and this can be used, right? This is what you want. You do not have to replace your bulbs too often, right? So you want your sources to have a very high lifetime, which these LEDs also have. Okay, thus what we have seen from these slides is LEDs are the sources which have got a tremendous luminous efficacy, and it also has a very good lifetime. And we can also look at this from this slide that we have here. So in this slide we are showing, if we look at the production of these sources, what will be the percentage of LEDs in the coming years. So if we look at that, you can see that my pointer is not moving as I want it to be, that by 2021 you have these LEDs. So these blue things are LEDs. So the blue bars, no, sorry. So these brown things, so these brown bars are for LEDs. So you would see in 2021, we will be producing a lot of LEDs compared to other sources. So we will have around 2 billion units of LEDs that will be produced by 2021. That means these sources are becoming popular. So this picture is just telling us the popularity of these sources. Earlier in 2030, the LEDs were not very popular sources. We had very small units of them produced worldwide, but by 2021 we will have significant number of LEDs that would be produced, and this just tells us that LEDs will be becoming more and more popular. Okay, so industries is also favoring LEDs, so we can understand this from this picture. Okay, so what are various different kinds of LEDs that we have? We have phosphorus coated LEDs, we have red, green, blue LEDs, we have micro LEDs, we have organic LEDs. Okay, so various flavors of LEDs are available. At IIT Delhi, we have been focusing only on phosphorus coated LEDs. Why? Because this is the one that you use at your home for illumination purposes, and it is obvious that if we can use them, nothing like it, right? Red, green, blue LEDs are also becoming popular because they have higher bandwidth. You understand what is bandwidth, right? So the source, if it has higher bandwidth, it can give you more data rate, right? So these red, green, blue LEDs has higher bandwidth. Micro LEDs has a terrifically high bandwidth. Organic LEDs are not so good at bandwidth, but from the bandwidth perspective, micro LEDs are good. But luminous efficacy of micro LEDs is not great. They have a very poor luminous efficacy, and thus they will not be used for illumination at your homes. Okay, they will be used only for biosensors and for these kind of applications. So of course micro LEDs is gone out of picture. So what remains is typically these organic LEDs also have a poor luminous efficacy. They also have a poor bandwidth. So we will also not be interested in these organic LEDs. So people have been using either phosphorus coated LEDs or red, green, blue LEDs for illumination and communication. We can use these red, green, blue LEDs, but the problem with them is that the communication system becomes complicated, right? Because you do not want to see red color at your home, right? What you want to see is white light. And so some effort has to be spent on producing white light in this source, which has these three different kinds of LEDs. Okay, so we will also not be focusing on red, green, blue LEDs, and the primary reason is it makes the communication system more complicated. Okay, so what we stick with is phosphorus coated LEDs. So as I have indicated that these two phosphorus coated LEDs and red, green, blue LEDs, they are typically used for communication, and organic and micro LEDs, they can be used for display purpose or for sensor applications. So we only be talking about communication, and specifically we will only be talking about phosphorus coated LEDs because it's simple. Now we have seen one problem with this phosphorus coated LEDs is it has got low bandwidth. Let us try to understand why is that. So how is white light produced when we use phosphorus coated LEDs? So blue light hit phosphor and phosphorescence happens, which produces yellow light and blue light. So yellow light and blue light mixes up to give you what is known as white light. Okay, and this process, this phosphorescence is a slow process. Okay, what does it mean? It means that the yellow light that is produced has a very terrible bandwidth. Okay, so what you can do at your receiver, you can use a blue filter. So blue filter only allows blue light to pass through. Thus, at the receiver, we kills this yellow light by using a blue filter. We only allow blue light to pass through, and in the process, it also kills the effect of phosphorescence, which is a very slow process, which leads to poor bandwidth of these LEDs. Okay, so by using this combination of phosphorus coated LEDs together with blue filter at the receiver, you can scale up the bandwidth of these phosphorus coated LEDs. So from 3-4 megahertz, it may become 50 megahertz to 100 megahertz and so on. Okay, so this disadvantage of phosphorus coated LEDs can be get rid of. That's what I say. It kills effect of slow phosphorescence and it imparts higher bandwidth. The bandwidth can become up to 100 megahertz. Now we have looked at VLC. We are interested in VLC, which means we will be using light emitting diodes. And we have answered the question, why LEDs? Because we are looking at higher reliability and energy efficiency. And phosphorus coated LEDs with blue filter looks like a good option. At least you can get 100 of megabit per second over these communication systems. Now let us understand the motivation behind VLC. We have already looked at one motivation. We are trying to establish a communication system together with an illumination system, and we want to get the job done by using the common infrastructure for these two applications. Together with that, there are other applications of or other motivations of VLC. We know that the RF spectrum is getting regulated, right? So suppose you want to have 100 Mbps over Wi-Fi system, or maybe 1 Gbps over Wi-Fi system. Typically 1 Gbps over Wi-Fi system, that means you would go to higher frequencies. You may be going to 2.4 gigahertz, you may be going to 28 gigahertz, or maybe 60 gigahertz Wi-Fi systems. Okay, and these bandwidths are regulated. So that means you have to pay for these bandwidths. And RF spectrum in general is regulated. There are some free bands here and there, but more or less it is regulated. That means we have to pay to use these RF frequencies. When this Internet of Things will arrive and when we will have a lot of devices, this RF spectrum will, of course, will face capacity crunch. Then we also know that this RF spectrum also has a very high susceptibility to electromagnetic interference. Okay, so if you operate a microwave at your home, then you would see your Wi-Fi connection drops down. Okay, that means it can be influenced by electrical devices that we have at our homes, right? And one very good advantage of this visible light communication is that the visible light does not go outside your room. So whatever light comes from this LEDs remains within this room, right? So it doesn't go out of the room. That means the signal stays within a room. That means it's a very secure system. No eavesdropper can listen to your signal, because generally what happens when you are talking over Wi-Fi, this signal is available to a lot of your neighbors. So if your neighbors are intelligent, they probably can eavesdrop what you are talking and who you are talking to. But that facility is not available in Li-Fi or in VLC, because the signal stays inside your room. Okay, so it's a very secure system. Also, this means that we can especially reuse the signal. For example, if there are 10 rooms in your house and the signal stays inside one room, then you can use 10 parallel links. You can imagine this is 10 parallel links. You can talk, all 10 people can talk without interfering with each other. But that is not the case in Wi-Fi. In Wi-Fi, because we are talking on the same radio frequency, and this radio frequency reaches to all the users in the home at the same time, when you talk, we compete for the resources, right? But in Li-Fi, this competition is not there. If there is one person in a room, that person doesn't have to compete with anyone else. Okay, so we can especially reuse this Li-Fi infrastructure. It's safe. It's safe because the human beings have been exposed to the light rays for ages. We have been exposed to sunlight for ages, and we know that it doesn't cause any health concerns whatsoever. On the other hand, still people don't know what is the impact of these 5G frequencies or 6G frequencies on human body. How does human body reacts to these frequencies? Okay, so it's also health safe. It's energy efficient, as I've already talked about. It has a very good luminous efficacy. Together with that, it is anyway being used for illumination purposes. So it's energy efficient. And finally, the thing that we have talked already, that it can be integrated with existing lightning infrastructure. So these are some motivations behind VLC, and looking at these motivations, what I feel is VLC will become a reality maybe in 10 years from now. It's not so popular nowadays, but in 10 years from now, if you want me to name one technology that will be available that is not currently available, this technology is Li-Fi or visible light communication. So it's a good time to research on this technology at this point. Applications of visible light communication, there are many. You can use for indoor wireless communication. You can use this in RF interference sensitive places. You can make secure systems using it. You can do some data loading of Wi-Fi. You can use this for energy harvesting, for indoor positioning, for underwater communication, for ad hoc networking, to make alert systems, and so on and so forth. You can imagine all the applications that you can think about. VLC may find its place somewhere. Okay, so these are various applications of visible light communication. Now let us try to get slightly technical. So let us look at the VLC system model. And VLC system model, that means we are looking at the LED characteristics. Let us try to understand this. I have tried to simplify the slide as much as possible. Still, if you have some difficulty, then we can discuss this. So typically in LEDs, what happens is we provide certain current, and this current is converted into lumens or flux or power or intensity, whatever you want to call that. Okay, so all these things are proportional to each other. So you supply this certain current and you get power. Of course, it's a diode, so the amplitudes of the current has to be positive. Okay, otherwise those things will be clipped off. So typically in LED characteristics is like this. You have power for a current, and this behaves more or less linearly. So you can see this function is more or less linear. It's not 100% linear, but it is more or less linear. That means it can be a source suitable for analog communication as well as for digital communication. For digital communication, of course, we do not care much about the non-linearity, but for analog communication, we care about the non-linearity. Okay, so this source, this LED can be used both for analog communication or digital communication. So typically what I'm saying is this PT, the power that the LED transmits, this is proportional to current IT, right? And this current IT is something like this. This is my information signal. So this SK are the for digital communication. This is the model for digital communication. So SKs are the symbols that we want to transmit. For example, for on-off keying, SK may take a value 1 and 0, right? For quadrature amplitude modulation, you have to think whether these SKs can be complex or not. We will come to that. Okay, at this moment, let us assume these SKs are real values, real amplitudes. Okay, and what are these PT minus KT? PT minus KTs are orthogonal pulse shapes, right? So you have a amplitude, you multiply with a pulse shape. Okay, then you have another amplitude and you multiply with an orthogonal pulse, right? So these pulses are shifted by integer multiples of capital T. So that means you have one symbol transmitted at every capital T. What is the data rate of this system? Data rate is 1 by T, right? So we are transmitting a symbol at every capital T. So this is my information signal, okay? And this information signal comes in the form of the current, and this current produces the suitable power, okay? Now we know that this current IT has to be positive because it's a diode, right? So this is one restriction on what can be IT, okay? Now there is one restriction that is not there in normal RF communication. In RF communication, you can have IT even negative, but in optical communication, especially if we are using LEDs and lasers, both are diodes. So we have the current to be positive. Now LED, if we like to understand the characteristics of LED, it is not an oscillator. So typically you might have seen in amplitude modulation, if you have a message signal empty, what happens? Let me see if I can write. So if you have a message signal empty, typically in amplitude modulation or in RF, you would have seen that you can multiply this empty with cos omega t or cos omega ct, right? So for this, you need a source which produces cos omega ct. Okay, and if a source produces this cos omega ct, this source is known as oscillator. So for amplitude modulation and for other forms of modulation, typically in RF we need oscillators. So you have a message signal, you have an oscillator which is producing cos omega ct, and you multiply this message signal with this cos omega ct. Now when you have this oscillator, just let us concentrate on oscillator, something that produces this cos omega ct, what do you assume, right? So if I have a source, let us I have a source which is oscillator, that means it produces cos omega ct. Now if I ask you what is the phase of this signal, so phase of the signal is omega ct. Okay, so if I ask you what is the phase at time t equals to 0.5, you immediately know this, right? The phase is omega c times 0.5. You can tell me the phase at all time instances, right? That means we can talk, if we want to talk about this source, we can say this is a coherent source. Why is this a coherent source? Because the phase of this source is known at all time instances to us. When we are looking at LED, it is not an oscillator. You cannot have cos omega naught t or sin omega naught t produced by an LED. It's not possible because this is a non-coherent source. You do not know the source or you do not know the electric field that is produced by the LED, what phases will it have at a particular instance of time. Okay, so this is what we have to understand, that typically laser is also not a perfectly coherent source, but LED, forget this at all. Do not at all treat this as a source which can produce cos omega naught t or sin omega naught t. So it simply means, what does it mean? It simply means that the electric field that is produced by this LEDs, it cannot be complex. When I say electric field is complex, what does I mean? It means that electric field ET can be written as ERT plus J EIT. What is the meaning of this? See, in reality, nothing can be complex and nothing can be complicated as well. Everything has to be simple. So simply, when you say something as complex, always it means that it is just used for mathematical ease. So when we are using mathematics, it is easier to talk about complex quantities and it's easier to manipulate complex quantities, and that's why we introduce these complex quantities. In reality, what it means, you cannot have ET something like this. Okay, so ET cannot be ERT cos omega naught t minus EIT sin omega naught t. If ET is like this, then you can express for mathematical ease ET as a complex quantity. Okay, so because this is not a coherent source, we do not know its phase at any time instance, so we cannot say this as cos omega naught t or sin omega naught t kind of source. So my electric field cannot be complex. Okay, I hope you understand this. Think more about this. That means, what does it mean? It means that the complex modulations are not possible over LEDs. Okay, complex modulations are not possible. So if we want to do quadrature amplitude modulation, in quadrature amplitude modulation, what would happen? We would have IT, we will multiply this with cos omega t, and we will have another current stream, and we will multiply this with sine omega t, right? This is quadrature amplitude modulation, and you may add or subtract. Now to do quadrature amplitude modulation, what we want oscillators. LED is not an oscillator, so you cannot have any complex modulation scheme possible using LEDs. So typically when we are using LEDs as sources, we are restricted to intensity modulation, simple on off key. You can have a pulse or you can have no pulse. Nothing more can be done when we are using LEDs. So the only two modulation formats that are available when we are using LEDs as a sources is we can use OK, on off keying, or we can use PPM, pulse position modulation. Okay, so these are two restrictions that we have got when we are using LEDs as the source. Of course, but IT can be complex. This the current that you are feeding to LEDs. This can be complex. What does it mean that this can be complex? That means IT can be something like this. Okay, this omega r and sine omega r. Omega r may be typically a smaller frequency. Okay, so you can generate IT. So this is a real signal, no problem. And as long as the entire signal is positive, that we have to remember, the entire signal has to be positive. As long as the entire signal is positive, no problem. But the signal that you're feeding to LEDs can be a complex signal, or it can be built using sines and cosine terms. So this IT that you can feed to LEDs can be generated using orthogonal frequency division multiplexing and so on. Okay, so now we have understood about the sources. So we know that IT is something like this. Power that is produced by the LEDs depends upon this IT. In general, this is proportional to IT. And we pass this through a visible light communication system model, which is a wireless channel. It's a time varying wireless channel. We have to remember that. That means its impulse response is not constant. Its impulse response depends upon the time at which you are looking at the impulse response. Okay, so its impulse response is not constant. So normally you would have seen impulse responses h of t. Okay, so if you have a linear time invariant system, you give an impulse signal and the output is a constant signal. It will just be a function of time, but this output that you will get will be a constant signal, will be a fixed signal. Here, the output that you get, of course, it depends upon the time, but it also depends upon at which time instance you have applied an impulse. Okay, this function of these two things. So this is a linear time varying channel, LTV channel. Any wireless communication channel is like that. So you must have seen in wireless communication courses as well, we do not have to be afraid of this this kind of impulse response, because this is a linear anyway. Still the convolution can be done. So the output of this linear time varying channel, I will not discuss why is this. You can refer to any wireless communication book. This will be you can do a convolution like this and you can get YT output. Okay, and this output YT is also in a form of a power, and this power hits the photodiode and the photodiode produces the current for the power that is falling onto it, and this is proportional by this constant which is known as responsivity. Okay, so I will skip this these slides. Maybe I will come back to them if you have any questions. And maybe the interesting point here is, yeah, after this photodiode we can use a meshed filter, and you have a sampler at the output of the meshed filter, and the current that you get depends something like this. So this SK is produced here, and then you have this channel coefficient, and this depends upon the energy of the pulse shapes that you are using. Okay, so I will leave this slides. You can look at the slides, go through them more carefully, and I hope that you will you could follow these slides. So now let us, so the message of these slides is everything remains similar as in a wireless communication or as in a digital communication also. So typically my wireless channel is just a linear time varying channel. Then I have an LED which converts current to power, and then I have a photodiode which converts power to current. And if you do the usual mathematics, what you can again see is that in these current samples, you get again the signal or symbol that you have transmitted. Now let us look at the differences between a radio signal and IMDD link. IMDD stands for intensity modulation. So we have seen that over LEDs we can just simply modulate the intensity. Okay, intensity modulation, and DD stands for direct detection. Direct detection simply means that we are using photodiode, nothing else, nothing complicated. You just have a photodiode and you just have an LED. So this is direct detection. Something other than direct detection is coherent detection, which of course you cannot use over LEDs. So we are not talking about it. So we can use coherent detection when we are using lasers. Okay. So LED is not a coherent source, so this variant is not feasible. Anyway, these are certain details. So is the bandwidth regulated in radio systems? Yes, it's regulated, right? You know that that's why you have this 2G spectrum, 3G spectrum being auctioned, right? So bandwidth is regulated. Every operator gets a fixed chunk of bandwidth, fixed chunk of resources. In intensity modulation and in direct detection, we use optical frequencies, which so far have not been regulated. Okay, so it's compatible. It's worldwide compatible. You can make these systems almost for free, and you do not have to worry about it. Does the radio signal passes through walls? Yes, it passes through walls. This IMDD system does not pass through walls. The drawback of this is it's less coverage, but it is secured. You can have independent links in different rooms. So this has both good points and bad points. You must have seen multipath fading. That's a common phenomena that happens in radio systems. Right? So multipath fading, we can understand this something like this. You have a transmitter and a receiver, and the signal from the transmitter reaches through several paths at the receiver, and the signals can get constructive and destructive interference and so on and so forth. So you have fading. You can have either very less power received or you can have very high power received. Okay. In intensity modulation direct detection, we cannot have multipath fading. The reason is the receiver size is much larger than the wavelength of operation. Okay. So the size, so receiver is so big and wavelength is very small. Okay, so wavelength in optical communication systems, we are talking about 1 to 2 micrometer. So wavelengths are small. Okay, whereas the receiver size is in centimeter. So receivers is much larger than the wavelength size. So what would happen? So you may have multipath fading here, you may not have anything here, you may have fading here, means low received power here, low received power here, high power here, high power here, high power here, low power here, high power here. So there are a lot of constructive and destructive interferences that are taking place at the receiver, and overall we will have the average of all of it. So effectively there is no fading in IMDD link. Multipath distortion is there in radio signals. It's also there in IMDD link. That means suppose I am sending the pulse. This pulse can get broadened. So it may become like this, right? Because the pulse may arrive at the receiver by traveling through different paths. Okay. So this pulse can get broadened. Okay. So multipath distortion can be there in IMDD link, but fading not. Path loss in both these systems is high. Dominant noise in radio systems, it's basically the signal from other users. In IMDD link, it is basically the background light, the sunlight, for example, if we are talking about outdoor communication systems. Okay. Input in radio systems is amplitude. Input in IMDD systems is power. Signal to noise ratio. Signal to noise ratio is proportional to this quantity, right, in both these systems. And why is that? Because even though xt is power, but this power will be converted into current, and the current that will be produced by photodiode is proportional to xt. So current square is again this quantity. Okay, so signal to noise ratio is proportional to the same quantity in both these systems. What is its implication? Its implication is that because my power is xt and my signal to noise ratio is this, that means my transmitter power requirements would be higher. Why is that? Because, for example, let us assume that the attenuation in my channel is 10 dB in both radio and optical. Okay, and to maintain the same signal to noise ratio, the power here must be doubled, right? Because the power here is xt, whereas power here is the same quantity. So optical systems typically require higher transmitter power. Average power is proportional to this quantity. In this optical, this is this, because xt is the power, right? So what is its implication? We can choose xt with high peak to average ratio. So we want this to be high, this quantity to be high, because we want signal to noise ratio to be high, and we want this quantity to be small. So the peak to average power ratio can be high in optical communication systems compared to RF communication systems. Now let us look at the basic concept of visible light communication. So this picture is very simple. You are getting data from internet. You are feeding this to LED driver, which is driving LED lamp, and photo detector converts back. You can have some filters and receive replication. Now what we have to care about when we are designing VLC system model is, suppose you have this as an access point and you have this as an access point. What can happen? The signal from this access point can interfere with the signal from this access point. So there can be co-channel interference. Okay, we have to take care of this. Also, because the range of these LEDs is very small, because optical sources are much more directional than the radio sources. So this radius is typically much smaller in optical systems, and thus when you move in your home or in room or in a big hallway, then the handovers that happens in optical systems is much larger than in radio systems. Okay, so we have to take care of this user mobility. We have to take care of this co-channel interference. These are open areas of research. If some of you are interested, you can look at how to do handovers in Li-Fi systems and how can we take care of this co-channel interference. And what can also happen is two users might be under the same access point. What does this mean? That you need certain rules and regulations by which users can participate. Okay, so typically medium access control protocol is also required. So these are certain challenges specifically from the MAC layer point of view: user mobility, co-channel interference, and then we need a MAC. From physical layer, the challenges are dimming support. Why is this important? Because sometimes what we want is we need to switch off the lights, right, in your home, and still you want to receive internet. Okay, so still you want your phone to be connected to WhatsApp while you are sleeping, so that you do not miss important messages. So we want internet even while sleeping. So we want the systems to be, or the lights to be switched off. Still we want the connection internet to be working. So we want to have dimming support. That's one challenge. We need to get rid of flickering, because if the data rate is very small or there are long trains of ones and zeros, and if you're modulating LEDs, what might happen? The LEDs may begin to flicker, and that's bad. So flickering, we have to get rid of it. We have to enable dimming support. We have to maintain illumination. We have to work over this limited modulation bandwidth of LEDs. We have to look at this mobility, small coverage area. There might be some blockages, right? Because it's basically a line of sight communication. We have to take care of co-channel interference and field of view misalignment. Sometimes you may get out of the cell. So let us look at some results from our university. So remaining of the slides, I will be talking about the research work that has happened at IIT Delhi primarily. So the first thing when we are designing any communication system is to understand the channel. The channel is important to understand. What kind of channel do we have? And the visible light communication channel, if we have to model it, of course, you begin with an LED source and a receiver. And 2-3 things are important when we are looking at the channel. One thing is that there is a line of sight path that is typically available between a source and a receiver. The second thing is this signal may hit the wall and may get reflected. Okay. So sometimes you may have a non-line of sight path also. And in this non-line of sight path, there is one reflection available. What can happen is you can have a non-line of sight path with 2 reflections, or yeah, you can have non-line of sight with 3 reflections, 4 reflections, 5 reflections. So one point that we have to consider is how many reflections should we consider in a simulation model? Because of course you cannot simulate with 100 reflections or 200 reflections, otherwise the simulation model will become quite complicated. So first we have to identify how many reflections or how many reflections are adequate enough, okay, or how many reflections are sufficient to model the reality. That's the first question. The second question is, what we have seen, the performance depends upon this LED semi-angle. So this cone in which LED transmits can be characterized by its semi-angle. This is an important metric. So we have seen that this LED semi-angle decides upon this cone. Okay, so this is an important metric. So we have looked at certain numbers. So the room dimensions that we have considered is this. The transmitter receiver separation is this. LED semi-angle is this. Physical area of reflective wall elements is this. Photo detector area is this. And there are some other numbers. Okay. And what we are interested in finding is delay spread. So I will not go to the entire simulations in all of it. I will provide the link to research papers which you can read and become more familiar. So one thing that we are trying to find out is what is the delay spread. So delay spread typically means if you have an impulse at an input. So basically if my channel is linear time invariant, this is typically the delay spread of the channel, in simple words, in loose words. If you already know it, it's fine. If you don't know it, you can think it like this. Okay. So the delay spread is the width of the impulse response. Okay. So more is the width of the impulse response, less is the data rate that you can transmit over a given channel. So we want to understand what kind of delay spread do we have over these VLC channels. Okay, typically for a big room, 5 meters by 5 meters by 5 meters. Okay, let me look at the dimensions. Yeah, 5 meter by 5 meter into 3 meters. So typically for this room, what is the dimension? So what we have seen is it depends upon the number of reflections, k equals to 3. So k depends upon k is the number of reflections, and it depends upon the reflectivity. What is the reflectivity at the walls, right? So if you look at these purple colors. So these are with reflectivity 0.2, and this green one is with reflectivity 0.4, and so on and so forth. So reflectivity increases in this way. Now we have seen that if we have up to 3 reflections, so you cannot see any difference between when the number of reflections is 1 and 3, right, in this curve. So that means till 3 reflections is fine. We do not get a better estimate by having more reflections. Okay, so there's some difference when we consider number of reflections is 1 and 3, but the difference is not huge. Okay, so for this study we have considered up to 3 reflections, and what we feel is if we consider up to 3 reflections, that's going to be okay. Okay, you will not lose much. So the delay spread, one trend that we have seen is first it decreases, then it remains constant for a while, and then it increases. What we want in our communication system, we want in the communication system the delay spread to be as small as possible. So we get an smallest delay spread somewhere when the LED semi angle is between 10 to 15 degree. So that points to us that there is an optimum value of LED semi angle which the system designers must adopt, and this value is between 10 to 15 degree. Okay, so this is an important result. Delay spread also translates to coherence bandwidth. Okay, so let us look at what coherence bandwidth is available to us. So up to 30 gigahertz is easily available, and LED's bandwidth is 100 megahertz. So the major restrictions comes from the LEDs and not from the channel, and thus it's not of interest to us at least to use OFDM and so on and so forth. OFDM should be used when my channel is frequency selective, right? So clearly my channel is not frequency selective for the data rates that we are talking about. For 100 Mbps, the channel is not at all frequency selective. If you target 30 Gbps, 40 Gbps, you have to think how you can do this because of the limitations of LEDs. Okay. Other than that, it is fine, right? Channel doesn't pose major constraints. Okay. So we have also analyzed what is the average bit error rate. Again, it's smallest in the same neighborhood because delay spread is the smallest. Average BR is also smallest, and we have looked this BR may be a function of where the user is in the room, right? So you can have a maximum BR, you can have average BR, you can have minimum BR, and these 3 quantities are plotted in the slides. And for all these pictures, we are assuming maximum reflectivity or the worst case reflectivity of 0.8. Okay, I will skip these slides. I will take a break of 2 minutes and I will continue within 2 minutes. Is this okay?
Yes, sir. That's fine, sir.
Okay, are there some questions so far?
No, sir. There are no questions right now. No, not in the chat.
Okay. Yeah, so let us proceed now with the remaining of the presentation.
Okay.
So let us look at certain design requirements. So based on this study, we can also look at the design requirements. So let us assume that we have got a certain data rate that we want to achieve over the system, and we have a certain transmitted power or signal to noise ratio, a certain LED semi-angle, and certain room size. So these are typically the design requirements that we have. And design constraint is that we want to keep the maximum BER, so user can be anywhere in the room, and we want to satisfy BER of less than 10 to the power minus 4. That means at any point in time, he shouldn't have more bit errors than 10 to the power minus 4. So can we do this? So let us look at this. So if we choose the room size as 10 meters by 10 meters and 3 meters, if the transmitted power we choose as 10 dBm, that is 10 milliwatt, then we can look at this study, and you can see that to get a maximum BER of less than 10 to the power minus 4, you can get up to 0.9 Gbps without issues. Of course, we are not considering any LED bandwidth in this study. We are just focusing on the bandwidth constraint that is offered by the channel. And for this, the LED semi-angle has to be 20 degrees. Okay, so LED semi-angle depends also on the room size. So let us look at this picture. So the coherence bandwidth that we have for 10 meter by 10 meter by 3 meter room is again the highest at the LED semi-angle of 20 degree, and this is 0.96. Okay. So then we have understood the channel, and the major understanding that we have developed here is that the channel is relaxed. Okay, the channel has no problem. It has a coherence bandwidth in gigahertz at least, and it has a small delay spread. And so for 100, 200, 500, 600 Mbps data, no need to go to complicated modulation schemes. Your simple intensity modulation is good enough. Now let us look at the modulation schemes that can be used in VLC. So I have said that the modulation schemes that we need to use should support dimming and flickering. Okay, so flickering refers to the fluctuation of brightness of light. So sometimes if the low if the long streams of ones and zeros are available at your transmitter, you can see LED flickers like this, and this is really bad. So we do not want to do this. And typically for flicker mitigation, you can have what is known as run length coding. So you do not allow long trains of ones and zeros. You try to insert few ones when you see a lot of zeros. Okay, and when you see a lot of ones, you insert few zeros. Okay. Dimming is more challenging. Flickering is easier. Dimming is more challenging. And the way we want to do dimming is digitally. Digital dimming is important because if we try to do analog dimming, then it is a problem. Your LED characteristics themselves would change. We do not want to do that. Okay, so we want to do digital dimming, and the way to do this is to use modulation scheme like variable on-off keying. So typically you must have seen on-off keying. When we want to have dimming support, we want to do variable on-off keying. What is the meaning of this? It's simple. So you can look at this picture. This picture we can look, okay, and here we want to have 90% dimming. 90% light source should be turned on. Okay, so what we want to do? So normally in OK for bit 1, you have the full transmission, and for bit 0 you have nothing, right? So for OK, this is something like this. So normal OK will correspond to 50% dimming because half the time it is on. Okay, so now in variable on-off keying, what we will do is, even for bit 0, you would have transmission for a certain period, and for bit 1 you have, of course, you have the transmission for the entire period, but this purple color things will overlap. So in bit 0 also this part is present. Okay, so what we do is, when we want the dimming to be higher than 50%, what you do is you allow the bit 0 also to have certain transmissions. Is there any question on this?
Participants, you may ask the question if you have any.
Sir, please explain it again. Bit 1 represent and how bit 0?
Participant, can you repeat your question?
Sir? Hello.
You may write the question in the chat.
Okay. Okay.
Hello.
Yes, sir.
Yes.
Yes.
Afternoon, sir.
Uh,
Sir, actually, I have one question on LeFi that, as you explained, it would be difficult to operate in harsh weather condition or harsh lightning conditions. Okay. So how we can overcome that situation? If we are facing that situation, if I am using the LeFi network in a harsh weather condition, or there is a constant lightning condition, because in that case the photo detectors will not be able to detect the modulation of the light wave. So how we can overcome that situation?
So the Li-Fi networks, basically the one that we are talking in these slides, is basically for indoor communication. It's not for outdoor communication. Okay, so in outdoor communication you have to be careful about the weather conditions, but for indoor communication the weather conditions do not affect your transmission system so much. A simple answer to that. But I can also answer your question. If we are looking at free space optical communication, which is the mode of communication which can be used for outdoor scenario, then we have to replace these LEDs with lasers. And what you can do is, you can use some error control coding, you can use aperture averaging, and there are various methods which we can use in outdoor optical communication links to get rid of weather effect.
Okay, 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 sir. Okay.
Okay. So let us. Is there any other question?
sir, there is a question in the chat, sir.
I cannot. How can I look at the chat?
Sir, on the top right thing, there is an bubble. Just click that, otherwise I'll read the question for you, sir.
Yeah, I can read it.
Okay. Please explain about bit 0 and bit 1 transmission. This is a little bit confusing. After
Okay, I
that,
will explain.
in VOOK modulation, that is variable on-off keying, sir.
Yeah. So for bit 1, just so for bit 1, we have the entire transmission present. For bit 0, normally what we would have hoped is nothing to be present. Okay, but for bit 0 also we are transmitting for a certain time duration. So this will give us an average higher than 50%. So you can have 90% dimming. Now the problem with this approach, there is one downside of this, is the distance between the two signals. So normally for error performance, we calculate the distance between the two signals. The distance between the two signals only depends upon the green part, because green part is only different. The purple part is present in both the signals. Okay, so the distance between the two signals will reduce. So that's the downside of it, and we have. Now let us see how do we do 10%. So this is the case of 90% dimming. If we want to do 10, sorry, yeah, let us see how do we do 10% dimming. So in 10% dimming, of course, you do not have any transmission on 0 for bit 0. For bit 1, again, for certain duration, we do not transmit anything. Okay, so this case tells us how to do 10% dimming. So I see another question by Abhishek Gaur. How can we implement double inverse pulse position modulation using visible light communication link? So I do not know about this. So what we have done is we have implemented only variable on-off keying and variable pulse position modulation. I have to read and answer to you. So let us move ahead. I cannot move my slides for some reason. Yeah. So another variant is this variable pulse position modulation, which is similar in principle. So let us look at one example of this. In pulse position modulation, what happens? Let us assume that we have two slots. So in one slot, you transmit a pulse and you call this as bit 1. And for bit 0, you transmit the pulse in the another slot and you call this as bit 0. So this is pulse position modulation. In variable pulse position modulation, you can have some overlap, or you may have certain time slots where nothing is present. So of course, this will give you a lower dimming. Okay, so in this case, this is 20% dimming, and this case is for 60%. So again, by using pulse position modulation, and again by changing this time period for which the pulses overlap, you can affect their dimming levels. So typically we have implemented these kinds of modulation schemes in FPGA, and we have done some experiments on this. We will talk about this later. So we have also studied the power spectral densities of various modulation schemes because this was not done before. So you can see that the power spectral density depends upon the dimming factor. So gamma tells us what is the dimming factor. Okay, so it's a function of that. And also for ppm, the power spectral density looks like this. Power spectral density is important to estimate the bandwidth of these various systems. We have also looked at the bit error rate of these various modulation schemes, and you can see that BR is also a function of dimming level. And what dimming gives us the best BR? That dimming equals to 0.5 gives us the best BR, as expected, because distance in that case is the highest. Okay, so this is for VOK and this is for VPPM. And now we have also done this using equalization. So equalization helps us in getting rid of small intersymbol interferences that are available in the system. So using ZFE, zero forcing equalizers, we have again improved on the performance of these systems. Okay, so modulation schemes in combination with zero forcing equalizer. Now the last topic for this talk is using multiplexing techniques. So NOMA is a very popular multiplexing techniques even for radio frequencies, and we have been using this NOMA, non-orthogonal multiple access, for visible light communication as well. So one advantage of NOMA is that it gets a higher channel capacity compared to other multiplexing techniques, and that's why we have stuck to NOMA. Okay, so we are looking at power domain NOMA basically. So the two users signal is different in the power levels, and then we can use what is known as successive interference cancellation receiver at the receiver to decode the signal. I will not talk about the NOMA in detail. I assume that this is known to you, and if it is not, it's a very interesting thing. You can read about this So basically it is multiplexing based on a certain parameter. The parameter that we have chosen for this is the power levels. Okay, so it is something like MIMO. So again, you can decode the MIMO signal because the power levels of two users that you're getting is different because of the channel coefficients. So again, similar thing is NOMA. Here we deliberately do this. So one thing that we want to do in this NOMA, we have proposed fair power allocation scheme. How do we allocate different power levels to different users? That's one question that we need to answer. So we have used a philosophy that the BR for different users must be same. So every user must be having the same bit error rate performance. So we have calculated the power level for that, and this is the power allocation factor. Okay, so for example, if just one example, so suppose I have a transmitter and there are two users located. One user is located near and the second user is located far. So this user should be given more power. So P2, we know that should be larger than P1. And this factor by which it should be larger than P1 is the power allocation factor, which is, of course, should depend upon the channel coefficients and number of users and so on and so forth. So slightly complicated, but it could be derived easily. Okay, so this is the power allocation factor that we have derived. And we have compared with the existing power allocation schemes like gain ratio power allocation and normalized gain difference power allocation method. And we have seen that this power allocation scheme has got a better BR and a better throughput fairness compared to the existing schemes. So we have worked on the looking at the channel models for VLC. We have looked at the modulation and multiplexing schemes used in VLC, and finally we have built certain systems as well. So I will give you the demos of that. So this system was presented in 2019 IMC, Indian Mobile Congress. So I think it happened in Gurgaon. So here it was in 2019, so 2 years from now. So we are showing the video transmission using Li-Fi transmitters and receivers. So this module, what you see here, this is Li-Fi transmitter. It was completely developed from scratch at IIT Delhi, and this is a Li-Fi receiver. And we will show the video transmission over this. So this is the original signal. So this signal goes to this Li-Fi transmitter, and we receive this signal, and this signal is displayed. So this is the displayed signal, and this is the transmitted signal. Okay, so this is the demo. So we are receiving the signal faithfully. We are displaying it on a bigger screen, and now a person blocks. So we are creating the shadowing effect, and when a person blocks, of course the received video stops. Okay, and as the blockage is removed, we get the normal Li-Fi link back. So this demonstrates that Li-Fi communication works. Okay, and we have been able to do this, a video transmission over Li-Fi. Now let us look at the another demo. So this is at a much higher data rate, 20 Mbps. So here we are showing the transmission over Li-Fi links for 20 Mbps. So higher bandwidth signal we are transmitting. So this is our latest results. We have been using FPGAs and so on and so forth, trying out with complicated modulation schemes, increasing the number of PAM levels in the modulation, and we can do this. And the lens design is also an important criteria for Li-Fi systems. So in this demo, we are showing we have built a lens system which automatically tracks light and focuses light to the receiver. So here you can see that. So as we move as we move the mobile phone, it changes the light source, and at the same time this receiver also orients itself. Okay, so I will show the video again. So the mobile phone is producing light source, and as we are moving mobile phone, the light source direction changes and receiver orients itself to that. So this maintains the constant light at the photodiode. So this is the purpose of that. So in movable device, you need this. So if you want to read more about the reference, you can read about this latest Li-Fi standard, ITU G.991, which talks about how to develop high-speed indoor visible light communication transceiver. So this concludes my talk. If there are some questions, I will be happy to answer.
Thank you so much for such a nice and knowledgeable presentation. Sir, I have just one question.
Yes.
As you have discussed that there is a centralized MAC protocol mechanism in VLC links. So, sir, my point of question is that in centralized MAC protocol scheme, we have a centralized node, okay, which monitors the whole network. Suppose due to some network failure, my centralized node uh, gets failed, or due to some network issue there is some problem in the centralized node. So is there any recovery mechanism available so that my service may not get interrupted and I got the uninterrupted services? So is there any protocol, is there any recovery mechanism for that in VLC network?
Suppose what is the alternative of VLC at this moment? It is Wi-Fi, right? So suppose you switch off your Wi-Fi router, what happens? Do you still get internet? No. So if something happens to Wi-Fi router, you lose out on the internet, and there is no recovery mechanism for that. So similar problem would be in Li-Fi. If something happens to the central controller, then of course you would not have internet. Okay, your internet would be switched off. So all these recovery mechanisms are built. So they are not built at home level, but of course, if you go deeper into the network, you will have some recovery mechanisms inbuilt, and all these recovery mechanisms involves duplication of resources. So if instead of one Wi-Fi router, if you have two Wi-Fi router, then it is fine. Then you can do some clever things on that, and you can still have the connection. So similarly, for Li-Fi, I don't think anyone is working on the recovery mechanism as such, but you can think about the recovery possible in Li-Fi, because if you have, let's say, 2-3 bulbs in one single room, then if something happens to one bulb, still you can have the internet connectivity over the second bulb. So that kind of things are possible. But controllers, so for every home there will be only one controller. So one controller will be controlling everything. If something happens to that, then I'm afraid nothing can be done until and unless you begin duplicating even that too. But that will increase the cost for the user.
Okay, sir. Okay, thank you so much, sir, for the reply and answering the question.
Thank you. Thank you.
Good afternoon, sir.
Good afternoon, Garima.
Sir, I have a question, not from sir this topic of your research, from another topic of your research. I follow that, sir. So can I ask that, sir?
Yes, you can ask. If I am able to answer it, I will answer it.
Sir, sir, actually I'm reading your paper written by you and Sukriti Garg, sir. Novel dynamic bandwidth and wavelength allocation algorithm for energy efficient in TWDM phones, sir, and some
Yeah.
other papers related to that also, sir. Sir, in that paper, you have you have designed a TWDM phone network, and then you have incorporated the wavelength allocation algorithm using Omnet++.
Yes.
Sir, sir, in which software you have designed this TWDM phone system, sir?
So you yourself has mentioned. So Sukriti has designed everything in Omnet++.
Okay,
I
sir.
also
Sir,
I
that
also have,
TWDM system also designed in the Omnet++, sir.
yeah, I'm answering it. So I also had similar papers during my PhD on
Yes, sir.
TWDM on MAC protocol, but I used Riverbed modular for that. So currently we have also moved ourselves to that software, Riverbed modular. But Sukriti, while writing this paper, has done everything in Omnet++. So when you are asking, now you are asking two questions. So the MAC protocol of TWD has been designed in Omnet++, for that paper. However, if you're so Sukriti hasn't done anything on the physical layer, so she hasn't used
Okay,
any
sir.
model or any physical layer simulator of TWDF1. We have assumed
Okay, sir.
we are using that. So the physical layer TWDM pawn has not been designed by us in any software. Uh, However, there is one student who there are certain radio over fiber based networks. We have designed the physical layer of that in a software OptiSystem, which is available at IIT. Okay, so when you are simulating the MAC protocol, you do not have to design the physical layer network. The logical layer network is sufficient.
Okay, sir. So actually, I was thinking that you have designed that that in the for physical layer, and then you have incorporated the Omnet plus plus with the some OptiSystem or some other software. That's why I am
No, we
asking.
haven't done that. We haven't done that.
Okay, sir. Okay, sir. Thank you, sir.
Thank you.
Are there any more questions, participants? If you still have any questions, you can directly email to our expert or towards me so that I can forward the same. Sir, thank you. Really, it was really lightning to see your research and live videos of the same. It was a really wonderful talk, and our participants have gained a lot from you. So now I
Thank you.
officially ask, okay, sir. Now I ask our student Ashi to say a few words in your honor, sir.
Thank you. I will also like to thank the participants for attending my talk and the organizers for inviting me to give this talk. Thank you everyone so much.
I would like to thank you, sir, for your insightful presentation on Wi-Fi networks and for providing deep insight on visible light communication. It was a really nice and a very practical session. And thank you so much, sir, for this informative session.
Thank you. Thank you everyone.
So now we are closing our day 4, and we'll be again meeting towards the day 5 of our FDP tomorrow at sharp 10 a.m. So I request all of you to join 5 minutes before that, 10 a.m. And Dr. Sandeep Vijay will be talking about high-speed communication beyond thinking, that is paradigm shift from 5G to 6G. So I request all of you to join tomorrow. And the feedback forms will again be shared by email as well as WhatsApp. Thank you for joining for today.